There is a quiet assumption built into modern physics that the universe is stable, that the vacuum state we live in is the true, lowest energy configuration of reality, the bedrock beneath everything from atoms to galaxies. But buried inside the equations of the Standard Model is a disturbing alternative. The numbers suggest the universe may not be sitting in its lowest energy state at all. Instead, we may be suspended in a precarious, false vacuum, a temporary energy plateau that could, in principle, collapse without warning. And the trigger for this collapse is not a black hole, or a supernova, or some exotic cosmic event. It is a ghost-like quantum fluctuation, a particle blip so small and so rare that it could happen anywhere, at any time, without leaving us the slightest chance to react. The story begins with the Higgs field, the invisible energy field that gives mass to particles. When the Higgs boson was discovered in 2012, physicists expected its measured mass to slot neatly into theories that ensured cosmic stability. Instead, its mass of 125 GeV fell into a deeply unsettling range, a range that implies the Higgs potential may slope downward beyond what we think of as normal space. In other words, the universe might not be resting at the true bottom of its energy curve. It might only be balanced in a shallow trough, metastable and waiting for a quantum nudge. If that nudge ever arrived, the consequences would be absolute. A single quantum event, a random fluctuation, or a high-energy interaction could cause a tiny bubble of true vacuum to appear. Inside that bubble, the laws of physics would be different. The Higgs field would settle into its lower, natural value. Every particle that depends on the Higgs for its mass electrons, quarks, W and Z bosons, would change instantly. Chemistry would vanish. Atoms would fall apart. Light itself would behave differently, and the bubble would not stay small. It would expand outward at the speed of light, rewriting the universe as it went. Because it travels at light speed, there is no warning, no sign, no escape. One moment, everything is normal. The next, the vacuum wall sweeps through, and the physics that once defined our reality are replaced by something alien. This is vacuum metastability, the idea that the universe is balanced on a cosmic trapdoor, held in place by probabilities rather than permanence. Most physicists believe we are safe for unimaginable timescales, but the calculations remain uncomfortable. They imply that the stability of the universe is not guaranteed by design, but by luck. And when you look closely enough at the numbers, the Higgs boson itself becomes a hint that the ground beneath our feet may not be the ground at all, only a temporary shelf above a deeper abyss. To understand how the universe could end in an instant, you have to imagine the Higgs field not as an abstract concept, but as a landscape, a rolling terrain of hills and valleys that determines the behavior of every particle in existence. In this landscape, our universe sits in a valley that feels stable. Particles have mass. Forces behave predictably. The vacuum energy holds steady enough to let stars burn and galaxies form. But theoretical physics suggests that this valley might not be the deepest one. There could be a lower, truer valley hidden beneath a small energy ridge, a ridge so thin that quantum mechanics allows the universe to tunnel through it. This tunneling is the heart of the danger. Quantum fields do not behave like classical systems. They can slip through barriers instead of climbing over them. All it takes is an extraordinarily rare fluctuation, a moment where the Higgs field dips just low enough, in just the right region of space, for a bubble of true vacuum to form. The bubble could be subatomic in size, far smaller than a proton. But inside that bubble, everything we know collapses. The rules that govern particles change instantly because the Higgs field determines the masses and stability of the fundamental building blocks of matter. Once formed, that bubble cannot be contained. The difference in energy between the false vacuum and the true vacuum acts like a cosmic pressure gradient. The bubble wall accelerates outward, consuming the false vacuum around it. Nothing can outrun or resist it, not light, not gravity waves, not the structure of space-time itself. And because it expands at the speed of light, The moment the bubble appears, its fate is sealed into the future light cone. There is no observation possible before it arrives. No detection system, no defense. Even more unsettling is the trigger threshold. You might imagine that only catastrophic events, black hole collisions, supernovae, primordial cosmic conditions could set off such a collapse. But quantum mechanics says otherwise. The trigger could occur spontaneously in a region of empty space where no particles are present at all. The vacuum itself provides the instability. In that sense, the most dangerous places in the universe are not the energetic ones, but the quiet ones, the regions far from stars, matter, and radiation, where the Higgs field sits undisturbed and quantum fluctuations operate freely. And yet, the universe seems calm, stable, unthreatened. The cosmic background light tells us billions of years have passed without such a collapse sweeping across the cosmos. That suggests the ridge between the false vacuum and the true one is high enough to make tunneling extremely improbable on human or even stellar timescales. But improbable does not mean impossible. The math still permits it, the equations still predict it, and the existence of the Higgs boson in the mass range we observe points to a universe that is not perfectly stable, only metastable, balanced on a razor-thin line between endurance and annihilation. If a true vacuum bubble ever appeared, its arrival would not look like an explosion. It wouldn't resemble a supernova, a gamma-ray burst, or anything else the universe has ever produced. What happens instead is far stranger. The bubble doesn't just destroy matter, it redefines the basic rules that matter depends on. Inside the bubble, the Higgs field settles into a different value, and with it, the masses of particles, the strengths of forces, and even the stability of atoms are rewritten from the ground up. Imagine a boundary racing outward at the speed of light, but instead of fire or radiation, that boundary contains an entirely new version of physics. As it sweeps through space, protons may cease to exist. Electrons may no longer orbit nuclei. Photons may behave differently or fail to propagate at all. Even space-time geometry could deform as vacuum energy shifts. The laws that allowed stars to shine, planets to form, and chemistry to function simply vanish. Not because they're broken, but because the universe has switched operating systems. The terrifying part is not the destruction, it's the indifference. A vacuum decay bubble does not burn or crush or vaporize. It simply replaces everything with a new state where our form of matter is impossible. A galaxy consumed by such a bubble doesn't explode. It unravels, dissolving into a new physical regime that has no memory of what came before. From the outside, you would never see it coming. Space does not ripple. Light does not dim. The collapse gives no warning, because the bubble wall travels at exactly the speed of causality. The moment you register it, you are already inside it, and inside it, the familiar universe no longer exists. The mathematics behind this comes from quantum field theory and general relativity working together. A true vacuum has lower energy than our current vacuum. That difference acts like negative pressure, driving the bubble's expansion. And because the speed of light is the maximum speed for information transfer, nothing can outrun the boundary or send a signal ahead of it. The bubble becomes a perfect, unstoppable cosmic frontier. There is also a subtle consequence that few people consider. A vacuum transition bubble does not just rewrite physics locally, it rewrites the future of space-time itself. Entire branches of cosmic evolution are cut off. The path the universe was on toward cooling stars, fading galaxies, eventual heat death disappears. In its place, a new trajectory emerges, determined by the properties of the true vacuum. Maybe it leads to a universe without stable atoms. Maybe it leads to one where structure forms more efficiently. Or maybe it leads to a universe that cannot support complexity at all. From our perspective, though, the question is not what happens after the bubble passes. It's that we will never have the chance to witness it. Vacuum decay is the purest form of a cosmic event horizon. Absolute, silent, instantaneous, and final. When physicists calculated the mass of the Higgs boson in 2012, they didn't expect the number that came back. It wasn't just a measurement, it was a warning. The Higgs mass, combined with the mass of the top quark, placed our universe in a narrow, precarious zone called metastability. Not stable, not doomed. Balanced on a razor's edge, where the vacuum we live in is only temporarily the lowest energy state. The equations imply that a deeper vacuum exists, a more fundamental configuration of the Higgs field, and that quantum fluctuations could overthrow our current one. This is the heart of the vacuum metastability problem. The universe looks stable enough to have lasted 13.8 billion years. Yet the mathematics of the standard model suggests it may be balanced above a deeper well. And that, well, if accessed even once anywhere in the observable cosmos, would begin the chain reaction that consumes everything. The instability arises because the Higgs field determines the mass of particles. A slightly higher or lower Higgs value means a universe with different chemistry, different nuclear forces, and possibly no complexity at all. When we plot the Higgs potential, the energy landscape of the field, it resembles a valley with a hidden drop-off. Our vacuum sits in a shallow landing, but the curve slopes downward again somewhere far beyond it. That deeper valley is the true vacuum. And according to current measurements, nothing forbids the universe from tunneling into it. Quantum tunneling is the mechanism that makes metastability dangerous. It allows the Higgs field, in extremely rare circumstances, to fluctuate into a configuration that seeds a true vacuum bubble. The probability is extraordinarily low at any moment, but not zero. Over infinite time, even the most improbable event becomes inevitable. And if high-energy events in the early universe came close to triggering such a transition, the fact that we exist means only one thing: we got lucky. Some theorists propose that unknown physics must intervene to stabilize the vacuum, perhaps new particles, supersymmetric partners, or hidden fields that reshape the Higgs potential. Others argue the metastability might be real but harmless, because the early universe's inflation smoothed out any dangerous fluctuations. And a few take the measurements at face value. The universe is unstable, but the decay timescale is so long that billions of trillions of years may pass before the first bubble forms. Yet the math leaves room for discomfort. Even tiny adjustments to the top quark mass shift the universe between stability, metastability, and instant doom. A variation of just one part in 1,000 flips the fate of reality itself. That sensitivity suggests the universe is not sitting safely in a designed minimum, it's teetering near a boundary. And here's the truly unsettling part. No law of physics guarantees that the universe must remain in its current vacuum. Nothing forbids it from falling to a deeper state. The only question is whether that fall happens so slowly that no civilization ever witnesses it, or whether nature already rolled the dice, and the bubble is simply too far away for its arrival to have reached us yet. If a true vacuum bubble were ever to appear, nothing could stop what comes next. There is no warning, no precursor signal, no physics strong enough to resist it. At the boundary of the bubble, the laws of nature themselves would be rewritten. The Higgs field would settle into a new value, one that redefines particle masses, rewires nuclear forces, and alters the structure of spacetime. This boundary would expand outward at essentially the speed of light, outracing every possible detector, message, or escape attempt. By the time any observer realized what had begun, they would already be inside the bubble and inside a different universe. What makes vacuum decay uniquely terrifying is that it is not destruction by heat, collapse, or explosion. Instead, it is a transition. The atoms that make up matter would no longer be bound the same way. Electrons might not orbit nuclei. Quarks might not form protons. Chemistry as we know it could simply stop existing. Structures from stars to cells would disintegrate not from violence, but from incompatibility. The old rules would vanish, replaced by a new set that emerged from the Higgs field's new resting point. And yet, from the perspective of physics, nothing goes wrong. The bubble interior is stable. It is simply a universe with different constants. A universe that may or may not support complexity, structure, or life. The tragedy is not cosmic obliteration. It is that everything familiar becomes impossible. Researchers often describe vacuum decay as the ultimate fail state of the Standard Model because it arises directly from the known equations. No new physics is required, no exotic particles, no speculative theories. Based solely on the measured masses of the Higgs boson and the top quark, vacuum decay is not just allowed, it may be the natural endpoint of our universe. Some physicists argue we should not take this too literally. Perhaps unknown forces stabilize the Higgs potential at high energies. Perhaps quantum gravity effects reshape the landscape entirely. Perhaps our vacuum is part of a deeper multiverse structure where metastability is normal. But these possibilities are hopeful conjectures, not confirmed safeguards. If the universe truly sits in a metastable vacuum, then its future is neither heat death nor collapse. It is replacement, a silent, unstoppable rewriting of reality, beginning from a single, microscopic event. And the ultimate irony is this: if such a bubble is already expanding toward us somewhere in the universe, we will never know. No signal travels faster than its horizon. No warning outruns the speed of light. The universe could end not with a dramatic cosmic finale, but with a whisper, an instantaneous slip into a version of physics where everything we understand simply ceases to apply.